Okay, Delaney, this is hopefully going to be a short video. We got 9 and 10 left on section 3.3 that we got to go through. Oh, gosh, this is a long section. All right, there's homework if you need that. I think we only have like 2 problems left on homework if you've been keeping up the whole time or whatever. Example 9 is where we're at, though. So here's the deal. We want just the domain. All right, let's talk about how to graph, again, like a log function. So real quick. Oh, gosh, why is that so thick? Let's fix that. There we go. Because Brady was messing around. All right, whatever. Okay, so there's that. Okay, let's say I have 2 to the x power. Okay, let's just pretend because that's that. All right, 2 to the x power. Every exponential function until I move them around is going to go through 1 and is going to have a ha at 0. So he's going to look like this. Whoop. But then if I flip him around and make him log base 2 of x, right, which is the opposite of this guy, he's going to go through what?
Negative. He's going to be reflected over y equals x.
So this dot goes where?
2. -1.
He goes to?
2.
No. He's at positive 1 this way.
Negative. Or positive 1.
He goes to positive 1 over here. And instead of a ha, he has a ba, okay? And he looks like, whoop, like that. That's what log base 2 of x is, okay? Log base 4 of x, or log base whatever of x, log base 10, this guy's log base 10. Log base 10 will be like this, but steeper, right? Kind of like an exponential function, he'll be steeper, but he'll still go through that dot, right? Okay, so logs look like the pink one. Okay, so this guy, now we just have to decide what does the 2 do and what does the 4 do?
Left 4.
Left 4.
Vertical stretch.
Okay, and he is not a vertical stretch. This is a horizontal compression, which a lot of times looks like a vertical stretch. But he's a horizontal compression, okay? He's a horizontal compression by how much?
2.
Half, okay? So, that means we're going off of this pink one, right? We're going off of this pink one. And I'm horizontally compressing him, which means I'm going to shove him this way and this way. There's nothing over here to even shove, so we're really just shoving him this way. And he's going to be half as close, right? So where does this dot move to? 0.5. He's now at the halvesy mark, right? Okay? So now he's going like this instead, right? And the plus 4 moves him to the left 4. So now instead of being at the halvesy mark, he's going to be to the left 4. Like 1, 2, 3, 4 right there, right? And he's going to look like this, okay? Where is this vertical asymptote at? -4. Okay, that's the important part. So what we've got going on here is, let me graph him so he's better. We have a vertical asymptote at -4 right here, and he is touching at -3.5, and he's doing one of these, right? Because he's shoved in, and there's a vertical asymptote at -4. They want the domain. Domain is left and right. Will he go to the left forever? Yeah, he will only go as far as -4. Will he touch -4?
No.
So he is a paren and a paren. -4 to infinity. There he is. Yeah? Okay. Okay. All right. Okay, we got to graph this guy, ln, and ln is what? Log base e. So fix him. I don't like the way that this is written because I like to write the x first. So this is written as -x plus 5. Okie dokie.
Reflecting.
Yeah. All right, so I'm going to graph what he looks like normally. Log base e is going to touch here at 1, no matter what, right? He's going to touch there at 1. He's just going to be the steepness of him, whatever, right? That's what he normally looks like. All right, so how does the negative flip him? Across the y-axis. So now he looks like this. And the 5 moves him to the left 5. So 1, 2, 3, 4, 5 to the left 5, and he goes like this. What point is he touching right here? -6, right? But his vertical asymptote is at -5. So what's the domain of this guy?
Negative infinity.
2? -5. Negative infinity to -5. That's the domain. Okay, that's what he will look like. All right. I don't like the last one. Let's skip it.
Yay.
Whoop.
Hooray.
Hooray, because he's x squared and I don't like that. Okay, but we've got to do some story problems, some pH stuff, okay? So we've talked about, I think I put at the top of this section. I'm going to make you dizzy, sorry. I put at the top of this section, yeah, right here. Exponential functions are used in banking, in population, in economics, and radioactive decay. The inverse of that would be log functions. That's used on the Richter scale and for pH and probably more things than that, but those are the two main ones, right? We're going to see an example of a pH and or Richter scale thing right now. Last problem. Okay, log functions and applications measuring pH, earthquake, that's Richter scale. Oh, and loudness. That was one thing that's not on my list, okay? Loudness, okay? So like the decibel scale is measured in terms of logs, okay? All right, intensity, right? Have we heard of intensity before? Is that physics-ish? Okay. All right, so example 10. Use a log function in an application. All right, I'm going to read the story problem and let's figure out what is what. The intensity I, okay, so I'm going to write over here. I equals intensity of an earthquake is measured by a seismograph. Have you heard that before? Okay, a device that measures amplitudes of shock waves. I naught is the minimum intensity. So I0 is min intensity. Okay. Now, a 0 level earthquake means there's no earthquake, right? Like there's basically nothing. I think it has to be like a level 3 before you can even feel it. Is that true? Have you heard that before? I think it has to be like a 3 or a 4 before you can even feel it. Okay. Yeah. Like we've had a couple of them in the last 2 years. I didn't feel them. I didn't feel either one of them.
I didn't feel it, but I heard it.
Yeah.
It sounded
I've heard about
like
people
really loud.
Yeah.
Outside.
Yeah.
That's what I thought it was.
Weird.
I had my head against the wall, and all of a sudden
And you
it
could
was,
feel
like,
it.
shaking.
Uh-huh. Isn't that crazy?
And then my dad
So there you
came
go.
home and he's like, "There's an earthquake." And I was
Yeah.
like,
Nice. So I naught is minimum intensity or a 0 level earthquake against which the intensity of other earthquakes may be compared. All right. The magnitude of an earthquake. So M equals magnitude. I'm just writing this stuff down so I don't have to reread the paragraph. Is given by this function right here. So we've got this thing going on. All right. Magnitude is the intensity over the minimum intensity because we have to be able to compare it to something, right? Like great intensity, but I need a number to compare it to. Determine the magnitude of the earthquake that devastated Haiti on January 12th of 2010 if the intensity was approximately 10 to the 7.0 times I naught. What?
10.7.
I'm trying to find the magnitude, right? Okay, so I've got log, and they say that the intensity is this many times I naught, right? So if I naught is, let's say 1, right? This is 10 to the 7.0, like times that, right? Okay, so we have our intensity versus the minimum intensity. We'll just put in 1 for minimum intensity, okay? All right, so hold on, ready? Look at this. What does this come out to be if I divide by 1? This is just 10 to the 7th power. This is log of 10 to the 7th power, right? Basically, what's the base of the log? 10. And what happens to log 10 and 10? Yeah, he's going to have a magnitude 7 earthquake. But that means the intensity of that earthquake is 10 to the 7th power. Do you know what 10 to the 7th power is? 1 with 7 zeros.
10 million.
10 million is the intensity of the earthquake. If it has a magnitude 7, it has a 10 million intensity, which is quite fierce.
It's just asking what the magnitude was.
Yeah. So this one, now that we kind of know what's going on, determine the magnitude of an earthquake that occurred near Washington, D.C. in 2011, and the intensity was 10 to the 5.8 times the initial intensity. Yeah. So if I do all that, the log cancels out. That's going to read as a 5.8 intensity, right? What do you get if you take 10 to the 5.8 power?
Oh,
No.
my bad.
A lot.
What's 10 to the 5.8 power? It's like
Oh,
actually, yeah, but it's actually like, doesn't have zeros on it. It's like a weird number. 10 to the 5.8 power. It is like 630,957.34. Okay, so 630,000 for an intensity. 631,000 for an intensity. Okay, So not near as intense as this one, which is a intensity of 7. But there's that, right? Okay. Like a 7 magnitude is way more than double a 5.8 magnitude. Does that make sense? Like 7 is not double 5.8, but 7 is more than double of the intensity of a 5.8, right? Because this is the intensity here and this is the intensity there. So weird how that works, right? Okay. How many more times intense was the earthquake that hit Haiti than the earthquake that hit Washington, D.C.? So how do I do that? We just talked about that,
10 million
right?
divided by 8.
Yeah, so it's 10 to, hold on. You don't need a calculator for this. 10 to the 7.0 power divided by 10 to the 5.8 power, okay? What do I do
Subtract.
when I'm doing, you subtract the exponents, right? Like I'm subtracting those exponents. So that is 10 to the 1.2 power. No, 2.2, 1.2 power. Yeah? What is 10 to the 1.2 power? 10 to the 1.2 power is 15.8. Yeah? So it is almost 16 times more intense. Like a 7 is 16 times more intense than a 5.8. Does that make sense? It's not double the intensity. It's not even like 1.5 the intensity. It's 16 times the intensity, right? Like that's how the numbers compound, right? Okay. Good?
Clean.
All right, there you go. That was example 10. Okay?
Can you go to
Yes, I'll go to the homework. Homework, and I think up to this point you should have been able to do everything up through except 72 and 96, but there's all of them. Okay? And I will give you the rest of the period to work, which is not a whole lot left because we have our maps testing today. Woo!
A through F. Kind of a lot of problems.
I'm sorry. I'm sorry.
It's okay, I guess.
Okay. There you go. She guesses. All right.
I know.
Okay. All right. Goodbye, Delaney. I hope you get to feeling better.